yesterday was a task one, right? The schematic design, the very beginning, very start point of the PCB design. So now you know how to do a schematic. And tonight will be the self-defined library. So what I really care about, let me take a look. Where is that? Here. All right, so the key points here, okay, is first, you need to know how to design a self-defined library by yourself from scratch, including the symbol and also the layout, and also make the connections between the symbol and layout. So the pin-to-pin connections. So this switch is a good example, even though it's just a through-hole example, but it still shows you how to do everything from scratch. It includes the measurement. You open up the data sheet and look at the dimensions, right? And then put them at the certain locations and name them and create a symbol, right? The symbol is very easy because all the switches, most of the switches looks the same as long as it has 3 terminals. But the tutorial asks you to draw a symbol by yourself. It's also a beneficial thing to work on. You have the symbol and the footprint is also designed, and then you make the connections from here, right? Make the connections, pin-to-pin connections. So you know how to design the library. And this is not the only way to do it. I could tell you maybe every 5 components I made in the library, probably only one of them was designed from scratch, because I just want to try to save my time, right? So a lot of times, most of the components can be reused, like the resistor, right? So the resistor symbol is always like this, 2 terminals. Doesn't matter it's a rod, doesn't matter it's a surface mount, and you have all different footprints, 0603, 1206, which is the one we use, right? So they all share the same symbol. So if you have one symbol available in your library, you can keep using the same symbol for different components. It just make the new connections to a new footprint, and then eventually rename the device as a different resistance for other things. It's really simple. I mean, this is just one example. Also for the op-amps, right? Op-amps are generally just as triangles, but you can look at the market, from DigiKey. They have all different footprints. Even the ones on our board, we probably have 2 different packages for our op-amps. It's the same concept, right? So the symbols are usually reusable, but the footprints are less, but still. There are certain names, so very typical types of footprints or packages. Probably packages is a better way to name it. Let's just say packages. It's being used for interchangeable. Sometimes it's saying it's a footprint, but footprint over here is not about the area of it, but the number of pins and also the arrangement of the pins. They call it footprint in Eagle, but in a general way of describing all the shapes, it's actually called package. So we are talking about this package, that package, the name of that package. For example, this guy, I think it's called ISO C3 or 4, I forgot. But they have all different names of packages. A thing, the shape like this, okay, with exactly the same pins, number of pins, and the same gaps and everything. It could be a voltage regulator. If you look at your Arduino board, they have voltage regulators on it. It's exactly the same shape. And for the one we are using here, it might be something else. Okay, so you can see the package's name is called SOT 223. Okay, 223. These are very typical packages. So you could, if you have this package or footprint available in the library, you could reuse it. Just create a different symbol and assemble it into a different device and rename it. Okay, so it becomes available in your library. Another way, right? For example, if you don't have it in any of the libraries, you download it, install it to Eagle, or you don't have any symbol for it. So the options are that you have to, if you don't have a symbol, you have to draw the symbol yourself. And usually draw a symbol is really easy, just lines, right? Lines and pins. And you could download the footprint from online, some of the websites. For example, Snap EDA, right? So Snap EDA, is that called Snap EDA? Yeah, Snap EDA. That's one of the examples. And if you see a footprint which is exactly the same as yours, as what you need, right? You can pick up the Eagle footprint and download it. So you will got a footprint in your library, or maybe just a library with both, right? Both symbols and footprints, like this, right? And you directly place it into your Eagle library folder directory, and then come back to your Eagle menu, right click and use it, right? Right click. There are several options. You use it, so this becomes a green light, a green dot, so it's available. Then you do a search, you will be able to find it, okay? And then you can directly just drag and drop into your design. Okay, this is one examples. But for this type of application, it's just so simple. There are only 2 through holes. You could just maybe just design it by yourself in a few minutes. It's not really tricky design, right? And then form a schematic like this. So I don't really care about the several details because this definitely came from a different class I taught somewhere else. You don't have to create exactly the same schematic as this, because this is the aim of, this schematic is to create a functioning PCB and fabricate it and make it functioning. But for ours, it's not. So it's just the goal is to let you guys go through the whole process and know all the key points of designing a functioning schematic. Like for example, you can see this switch. If you don't want to include this switch in there, it's fine. We are not using the same switch here. And also for the testing point, it's really beneficial to have a testing point like this. So if you go to the PCB of this schematic, these testing points are just the through holes, right? So it allows you to push your probe against that little metal piece, the through hole, and so you can probe it as a testing point. So this is something you can use for your schematic, right? When you're designing a circuit, you want to have some of the voltage nodes available to be probed, right? So you can set a through hole over there so you can probe it. And you can see several of you guys lost the points for the op-amp design, operational amplifiers over here. So the key point the reason that I want you guys to use this tutorial is that if you pay attention to these ones, you can see these are IC. See, so the IC is this device name. IC4 is the number 4. I may have 4, 5 different ICs of the same op-amp, but I can see that all the 4 over here that are being used for the same purpose, they came from the same IC. So that chip has 4 op-amps in it, and if it's being used for the same circuit, you should use all the 4 from the same chip. So for example, it's IC4 is that chip. It's A because it's the IC4's A op-amp, right? And then the second one is IC4's B op-amp, and then C, and D. So when you are placing these op-amps, if you place them in a certain sequence, don't cancel it and replace it. Just directly after you grab that component, just play it 1, 2, 3, 4. Don't stop, non-stop, okay? So in that case, you will be able to place these 4 A, B, C, and D from the same chip into the schematic. Even though this seems like there are 4 different devices, but actually if you jump to the layout, they are actually the same chip, just one chip. Okay. Then after the 4th one, if you keep placing, it will start from IC5. So this is handled by Eagle automatically. It's a really nice feature of it. Okay. So you keep placing after the 4th one, you keep placing another 4, and they will all labeled as IC5. And we'll start with A, B, C, D, right? If you do it keep doing it, it will be IC6, A, B, C, D. So one quick question: if you don't have to use 4 of them, you have one chip, right? You only need to use 2 of them, right? You keep placing A and B. Do you still have to place C and D in the schematic in order to make it error-free? Can you just ignore C and D if you only need the 2 of them? It will be fine, right? You don't have to keep placing 4 of them, right? But eventually, no matter 1, 2, or 3, or 4, you have placed in the schematic. Whenever you jump to the layout, it's going to be one chip over there. Okay, so that's the key point of using the op-amps. I think we probably do this very similar thing to your schematic, so it's good to pay attention to that. Okay. So power and ground, because all these four are in the same chip, so you basically just need the first one to be shorted to ground and power. And in the tutorial, it shows you how to do it. Have to do a right click and select the power rails and add a power and ground to it. So if you do one power and one ground for one of the symbols, all the rest three will be shorted by these VDD and grounds by default. You don't have to manually do it yourself. They will be shorted to it because they're in the same chip. Okay, keep in mind. If they're not in the same chip, you need to power them up and ground them separately. Any question on this? And I believe you all know that if you right click and name that trace with the one name and you name another trace somewhere else with the same name, they will be electrically shorted, right? You all know that, right? You don't really have to draw a physical line to connect them, because the same name will keep them shorted physically. Okay? Right, so if you look at the schedule here, tonight will be the self-defined library, and then you add a little more things to the schematic, then you will be done, right? And then Wednesday will be a PCB, right? Will be the PCB layout, so start this early, okay? Because the PCB, I'm going to require you guys to do a lot of manual layout instead of just directly running the auto router, which is usually giving you an ugly result. So you must do some sort of alignment. I cannot create a rubric over there because it's so subjective. But so you cannot just directly randomly place parts in different places. So at least for these resistors, obviously you can see these they have a direct connection. You want to place them, use this point towarding facing this point here. This is a direct connection. So you can imagine when you are drawing a connection, you can directly just left click and right click, right? So that's the goal. If there's a direct connection over here and you have to rotate it and place it in your layout, I'm going to take some points though, because it's so easy to rotate it and make a better connection, but you didn't choose to do so, right? You don't have to spend like 24 hours to make a perfect layout, but you just have to have some considerations in there, right? Instead of randomly placing everything in there, right? So that's a special resistor 1 ohm. It's a rod resistor. It's just so different from other ones. It's a low, high power current, running a lot of current. So that's why it's huge. But for all the other components, you can see, like I told you guys, the footprint of the parts could be there could be some standard packages that being used for that component. It could be, for example, the parts we are using in this one, since you already did the first schematic, right? So what's a very typical or standard package we are using for the resistors and capacitors in here? What is that? It could be in the interview. It could be an interview question. So what's the package we use the most? 1206, right?
Yes.
What does that mean?
It's the with the height.
Yeah, it's a 0.12 inches by 0.06 inches by size. So this is so before this semester, the last time probably was 2 years ago I taught this class. We all used 0603, the package. So it's a 0.06 by 0.03 inches, and I could do it really well, but students couldn't. So we chose this bigger one this time. So you already soldered it in the class. I didn't see a lot of issues with soldering these parts, right? But we did see issues about the microcontroller and the USB chip. But definitely not the capacitor and resistors. All of you did a good job. It's easy to handle. It's really nice. It's 1206, okay? 1206 surface mount. And do we need to know the package name of other components? Some of the really popular ones you may want to remember it, but I'm not going to put the name on the quiz right now. Like these one, for example, like something like this, right? You'll see a voltage regulator of this one on the Arduino Uno board, and you'll see some of like these ones. It could be a BJT, could be a voltage regulator. It's the same package but different components, right? Like this one, and these ones are the switches, I believe. mean, this PCB doesn't really have a lot of different packages, you know. So easier to handle, okay, easier to handle. All right, so Wednesday, this is, no, this is due Friday, I guess. The layout is due Friday. So this week is pretty much a PCB week. Keep that in mind. We do have other assignments, but they are not due until later time. I think the IR one, task 3, where we started 3 weeks ago, I think you have to get that done. I think when is that due? In class? Tuesday? Tomorrow? Homework 8. All right, it's tomorrow, right? But you can see I do give you guys time to work on the PCB design of your course project. You can see we are having a lecture on this one today, and for Wednesday and Friday, we'll directly meet in 610. So please come, okay? Even though we don't have a formal lecture for that, but I want to work with you guys on the PCB. So you work on the PCB and you ask me questions. It will be a in-person tutorial session, okay? Tutorial session, and also about your you can chat with me about your course project, because that proposal is due the 7th, okay? The Friday. It's Friday this week. That's a proposal due, right? And after that, the 10th will be Monday, and you need to get your software and hardware. Probably I'm gonna delay this for 2 days or 1 day or 2 days probably. Should I? Because the PCB is due on 14th, which is Friday next week. So which means you need to have a design, complete design of your course project on a Skyboard by Friday next week. Like I told you, I'm not asking for a very complex course project, keep in mind. So what I really want to see is a functioning PCB. So it could be a little tweak, no, it shouldn't, but could be a combination of 2 different modules on whatever you have learned, right? If you haven't learned SD card yet, you could also propose it. But let me see when I'm gonna teach that one. I think next week, probably. Yeah, next week on Monday, right? So Monday we'll go through that tutorial, so you can still include that one to a project. The reason we have to push this a little bit harder, because we do need to send it off for fabrication sooner than later. So okay guys, I can guarantee that you can receive the PCB before the deadline. So you can start working on assembling that, right? Don't want to delay this too much. So again, course project, combine 2 different modules on the from the Skyboard. Examples, for example, so for the microphone tutorial we're going to cover today, it's ask you guys to measure the frequency of your whistling. So if you can measure the frequency of the whistling, and you can add that frequency to your the light effects, right, of the RGB. So depending on the frequency, you can show different colors. That could be one, right? So combining RGB and the frequency measurement. I think the code will be just a little change to the whatever we are going to learn this week for the ADC one, right? And SD card, right? So you are actually playing back. You can actually record your voice and play it back to the speaker. So it's using SD card and speaker. You could add something else, like you can make a little game about it. A little button, right, to play a sound effect or something. You just think about it, and we can chat Wednesday and Friday or during office hours this week. Let's just get the ideas of the course project nailed this week. When is that due? Course proposal? It's Friday this week, right? So Friday midnight. Okay. You could also you can make minor changes after it. So don't worry too much about it, right? You can always add minor changes. But for programming, make sure that you have at least 2 ISRs and control the different states. You are doing state transitions instead of just one loop. Okay, think about that. All right, 10th will be Monday. Probably I will change it to Tuesday. Okay, I'll change it to Tuesday. So Tuesday will be your demo of the software on your Skyboard next week, Tuesday. All right, and then Friday next week will be the final PCB design, all right? I will expect your Gerber files of the PCB, and I will start sending things out on Saturday, or yeah, probably on Saturday, because they don't really break in China. They say I can do it. I can send it to their Saturday. They'll start probably fabricating it right away, and then we could probably receive them 24th. Okay, that's during the Thanksgiving break, right? And then after you come back from the break, you will have your board and you can start soldering things on it. Any questions on this, on the timeline? Pressure or too basic? No? Easy? Difficult? Pressure? Yeah. I mean, pressure is good as long as you guys are learning something. I mean, this is something I always ask myself: Are my students learning things that are helpful for their career? This is the most important thing. I mean, are you really learning something? This is okay. Cool. Anything else? Anything else on the schedule? Okay, so for the after you submitted the PCB for fabrication, I think we have a lot of time. You can see November 14th to the final design, the final presentation or report is due on the 22nd of December. It's about more than a month, so it's not a problem at all. But in between that, we have other tasks. So the reason we have to squeeze everything into the most recent 2 or 3 weeks is just because of the piece of fabrication, okay? And also there's a winter break, a full break. And you can see the schedule for the remaining 2 tutorials, right? We'll have 2 tutorials left. Good news, okay? So the one that we are, covering last week and this week is ADC and microphone, and then Wednesday and Friday will be just tutoring sessions, right? And then tutorial 7 will be the last one. So we'll learn SD card, SPI communication protocol, and the double buffering technique for logging data to the SD card and playing it back. So after that, on Wednesday, so I believe this will probably take 3 lectures, including a bunch of in-class exercise. So we'll do it Monday, Wednesday next week, and Friday I'll let you guys work on a course project, because that's the day your final design is due. So that's going to be a tutoring session in the lab. I'll stay there probably for more hours than my normal office hours to help you guys out. So make sure everyone can get a functioning PCB. Okay, and the 17th we'll have 1 more lecture to finish. I expect there will be 1 more lecture that we need to finish it, and then I'll give you Wednesday and Friday from that week to work on your SD card and SPI stuff. Okay, and then for break, then we'll do our assemblies, and that's everything about the semester. Okay, it's pretty tight. All right. So there's 1 more. I think I already gave it to you, right? The in-class number 12, and we were at in-class number 11 last time. We didn't finish everything, but let's come back to that one. Where we were at, number 6 or number 7? Number 7.
12.
What's that?
Can you go over number 16?
Sure. Okay. All right, so over the weekends, I just finished all the tutorials over here. I'm pretty happy that everything worked. You guys have pressure. I will have pressure as well. I'm developing a new course totally this semester based on the Skyboard. And I'm very happy this is the second last one, so then there will be the last one from the SD card one. I'm done. I'm just converting everything from the PIC version I taught at mines, and translate all the coding to Arduino's C programming. It's not very difficult, but there's a lot of time commitment in there. All right, so number 6. What is the common human whistling frequency? It's 2 to 4 kHz, and I did a lot of whistling over the weekend for the task tool, and mine is always 1.8 kHz or 1.9 kHz. Sometimes it reaches 2 kHz, but never go beyond that. If you are able to whistle at a higher pitch, then probably you are going to see like 3K, 4K, but mine is not. So expect it's like 1.5, 1.9K is normal. But you know, I googled it. It says it's 2 to 4 kHz, which is fine. Okay. So if we choose 25 microseconds per sample in our code, what is the sampling rate? We did the calculation. It's just 1 over 25 microseconds will give you 40 kHz. And how many ADC clock cycles are required to finish one conversion? And we talked about that on Friday. That was 13 cycles for the ADC we used here, right? So 13 cycles. And what's the largest prescaler we should use for this whistling experiment? 10 or less, right? Oh, 16 or less. Sorry, 16 or less. Is that 16 or less?
We said 30 last class.
30, that's for the frequency. But I'm talking about the prescaler. If I thought 30, that was wrong. Okay, go to, let's see. Oh yeah, 30 or less. But the thing is, we don't have 30, right? So the first one less than 30 is 16, right? So 32 or 16. So 30 or less, but the thing is we don't have 30 at all. So it's going to be 16 or less, actually. So we use 16 or less. Where's the table? It's over here. Here, this one, right? This one. So these are all the options for you guys. That's a clock. Frequency of the prescaler for the clock being put into the ADC inside the chip, right? It's not the prescaler for the major clock, but for the ADC's clock. So you can see it's 32, and the next one will be 16. So based on the calculation we did over here, right? So see, it's a 16 megahertz, and you divide it by the sampling frequency, which is 40K, and times 13. And the result is 30.78, right? So the prescaler should be only less than that. So the first one available in the table is 16. So I told you guys, I showed you on Friday that I tried all these prescalers, including 16, 8, 4. Did I try 2? Probably I didn't, but you can try it. So the trade-off here is, if you use a smaller prescaler, the accuracy of the conversion will be less. It's always a trade-off, right? So the accuracy will be less. But the thing is, if you just look at these results, you probably couldn't tell because it's getting smoothed out by the plotting, Excel sheet. But you can see that all the signals, the whistling signals, are being recovered, and they all look very similar. If you look into the details, maybe you could tell, these ones are not as smooth as the previous ones, but you couldn't get a really definitive answer about that actually. But at least you can tell all the signals are getting recovered. So which means whenever you're getting a prescaler smaller than 16 or 16 or smaller than 16, you can always recover you can always sample the signal correctly and recover the entire signal from plotting it in Excel or Python. Okay, but you can see if I choose different prescalers, you're getting an aliasing signal. It's alias, so they're same signal, same whistling, but giving you different results, which is wrong. It shouldn't, right? And this also asks you to capture that test point. So to measure if you are actually getting a 25 microseconds interrupt for the ADC sampling. So the way to do that is you plug in the test points here, see, in your ISR conversion 25 microseconds interrupt. So this is only just one line, right, just for that line. And you plug in a test point, the test pin high and test pin low. So whenever it gets into this ISR, it pulls it up, and after it finishes it, it pulls it down. So you are getting a little pulse. And then you can measure it from the rising edge of each pulse. That duration over here will be the same duration as the interrupt of the ADC sampling rate. Okay, so measure it. You can see I'm getting 26 microseconds. But actually, there are errors. If you zoom in further, you can probably see the cursor is not perfectly aligned to the rising edge. And if you tweak it a little bit, you're probably getting very close to 25 microseconds. So it was sampled at 25 microseconds, right? So you can verify it using the oscilloscope. So you need to do this in your report as well. Measure it. It could be a little bit tricky. I can tell you there's a better way to do it. For the triggering menu, you can trigger at the rising edge, you can define the duration, and eventually get a really reliable capture of it, and then you can measure it. However, I didn't do it. I didn't have time to explore how to do the triggering. So what I did is it keeps sampling, right? It keeps sampling. So you just have to, look at it and then press the run and stop at the right time. You may have to do it multiple times in order to capture this guy, but you will definitely be able to see it and capture it. And then you zoom in, you can measure it, okay? And then you adjust the time scale on the x-axis to zoom in and make it visible over there, okay? And take a picture of it. So remember, for task 1, I pretty much included all the code over here. Maybe just some of the variable declarations were not included. But for task 1, the 2 SRs are already provided. You can see this one will do the conversion, right? It takes 25 microseconds. So whenever this line is getting executed, the ADC conversion will get started, right? So it will, when that is done, it triggers the ADC completion SR, and so you can do the data store. You can log the data to the variables you want to store them in. Okay, and one information I think I gave to you, and that was a little bit inaccurate. I think that was problem number 3. Problem number 3. I think I told you that you have to read both, right, in a certain order on Friday. So I think I told you that if you, no matter you just need 8 bits or 10 bits of precision, you have to read both registers, which stores the ADC's results, and that was wrong. Sorry about that. So you can see the converted results will be stored in that ADC register. Where's that one? We're looking for that snapshot. Okay, this one, right? This one. So since we chose one for AD LAR, right? See this one? You have 2 options. You can right justify it, or you can left justify it. All right. Remember, if you right justify it, if you want to use the 10-bit, you need to shift your ADCH to where by how many bits? No, 8 to the left, right? To the left by 8 bits, and then you OR the result with this guy and stores them in a 10-bit result. That makes sense, right? Any question on that? We all need to know that. No questions, right? This will be on the quiz or exam in the future because this is so fundamental technique. In all the other digital chips you have to use in the future, if you got employed by a company and you read the data sheet, if you see the data is more than 8 bits, they will be stored in separate bytes, and you need to do the shifting and OR logic, right? It's really simple and fundamental operation. You just have to know how to do it. If everything is getting left justified, remember Luke asked that question: do we need to shift this 8 bits to the left by 2 bits? That's the question for that. So the answer is no, actually. If you need only 8 bits, you could just read ADCH without doing anything. If you need 10 bits, precision, what you need to do? Shift ADCH to where by how many bits? To left by how many bits? 2. What about the ADCL? No, you have to right shift by 8 bits. By 6 bits. And or it with the result of the ADCH. Let me write it down for you. Okay, so for example, we are doing a left. Let's do both, okay? Since this will be on the exam. So if for the first one, for the right justify, yeah, I know. For this right justify, you want to process it as this, as follows, right? So it's going to be ADCH, left shift by 8 bits, right? And then do a bitwise OR with ADCL. That's it. For right justify, you are not shifting the ADCL at all, but you have to left shift the 2 bits over here to the left by 8 bits. And we are assuming a 10-bit precision, right? For left justify, the bottom one, also a 10-bit precision. What should we do? For the bottom one, ADCH, left shift by 2, and ADCL, right shift by 6. Does that make sense? So we're basically shifting these 2 bits to these 2 bits. So it's a 6 bits, right? 6 bits of shifting. And for these 8 bits, you need to shift it to the left by 2 bits. And all these results should be this type. If the 8 bits, you are screwing up all these upper 2 bits over here. So you're actually tossing these 2 bits, right? So I have to 16 bits as a result. Okay, so I'm talking about 16-bit precision, but for 8-bit precision, we don't really need to use or even put ADCL in our code at all. You could directly just read it, right? Could be just 8-bit result. Let's just call it result. Done. That's it. Okay. For 10-bit precision, you have to read. For these 2, you have to read ADCL first. The reason for that is the digital designer of the company, of the microchip, they designed it in a way that after you read ADCH, they will update, they will put new data into ADCH. So you want to read ADCL first, so it's not updating your ADCH from the previous conversion, right? And then you read ADCH, then you read both. You don't care if it's getting changed after that. We couldn't see it, but the datasheet told us to do it that way. Okay? Does that make sense? So the question is why? Why this will work? a bit confusing, right? I mean, for here, for the 10-bit precision, we have to shift it. So seems like these stores data. I mean, if we just read these ones without shifting everything, are we dividing the result by 4? They're supposed to be shifted to the left, but we are not shifting them at all. Actually, it's not. For example, okay, if you read so the thing is, whenever you are just reading this guy and put everything in the 8-bit result, I'm not sure if there's a like little mechanism in the chip design they handled it in that way, but it's assuming that you are only using you're doing handling this guy as an 8-bit result. If you are, for example, you are reading 1 0 0 0 0 0 0 0, right? Reading this, it's an 8-bit result, and that's 50% of the full range. 50% of the full range, and the full range is 5 volts, and you're getting 2.5 volts. If you're doing this using 10 bits, and eventually you got 2 bits here, and then 1 2 3 4 1 2 3 4, still 10 bits. So this result will be still 50% of the 5 volts. So it's not actually changing the result. I mean, anyway, so the conclusion is that if we are only reading 8 bits, we only need an 8-bit precision. We can drop the lower 2 bits, and we can directly read from ADCH, and that's fine. All right, and I think that's everything for task 1. I already have everything included in here. So for the conversion, you'll see here, this is I haven't updated this yet, but you don't really need this line. I tested it during the weekend, so you can comment this out. It's not going to change the result. All right, and for task 2, for task 1, it's so this is your expected results.
This is for tutorial 6 and task 1. They collect and also whistle search sound, really similar to a sound wave. So I'm going to show you. So I'm going to show. I've turned it on. I've turned it on.
The thing is, I don't have a control for task 1. So whenever you turn on, you part it up, it will directly log. I think that's 64. How many is in there? Probably 64. 64 data points. It happens really fast if you think about the sampling rate. Okay, so what you want to do is you want to start that whistling before you part it up. It's a really silly way of doing that. So you start whistling, so the data keep going, right? You start it. It probably only take so fast, right? It will sample 64 points from your whistling, and directly log it to PuTTY, and then you copy and paste. You can see, I'll show you how I did it, okay? So I'm pushing that button to reset, because every time you reset it, the computer restarts, right? So it restarts to start loading the code, and it will sample that 64 points. That's for task 1. It's really simple. So I didn't add a lot of like control in it, like flags or other thing, anything else. So you restart it, it will load the code and sample that 64 points really quickly. Okay.
I want to restart it right away. Okay.
Okay, so the data is getting sampled over there. It's printed out into a PuTTY, and then you copy and paste into Excel sheet, and you plot it, so you can see a sound wave. If you see something else, things are going wrong. It could be either your whistling is not loud enough, so then just use a YouTube video, play the audio, so you don't have to whistle by yourself, and you have to move it very close to the microphone. So for example, the speaker of your phone playing that audio, you play it, you just move it probably no more than this much, right, next to your microphone, the microphone on the board, so you can get a decent sound wave. It should be a really a waveform that is very similar to a sound wave like this. Okay, do several times until you see. You can repeat my results over here. So that's for task 1. For task 2. I'm asking you guys to log more data over here. Instead of 16 or 64, I'm asking you guys to do 256. Log 256 data. And there will be multiple periods, for sure, multiple periods. And I'm asking you guys to measure the frequency of your whistling. All right. So you can see after getting all the data logged to here, and even though I haven't plotted yet, but you can see there are high points, low points, and it's kind of like a pattern. And if you see something like this, even though you don't plot it, you can tell it's probably a successful trail. Okay. And then you can also copy and paste into Excel sheet and plot it this way. This is not from YouTube. This is my whistling. And I'm not a robot. Could you imagine? It's like a sound wave just from your whistle. And I copied and pasted everything here, and you have to do it line by line. Actually, you can see this is the first line. I separated the data because they are not being separated by cells. So I separated all the cells and put them in different columns using that command I showed you over here. And then put them together. So I used the 4 lines, and so 4 lines is giving me probably 3 periods. 3 periods. And you can imagine there are another 12 lines of it. So it's 3 times 4. So if you whistle correctly, not correctly, I don't want to say that, but if you whistle in the normal way, I think you are probably expecting somewhere around 12 periods for 256 points. That's a benchmark you want to pay attention to. So if you're only getting 1 period, 2 periods, that means either your whistle is not loud enough or your code has something wrong with it. So if you whistle loud enough and close next to it, just right next to it, and you are seeing sound waves, it should be somewhere around like 9 to 12, 13 periods. Okay? And the code will do the calculations and find out the periods and the frequencies. So my whistling frequency is 1.983 hertz, kHz. It's very close to 2 kHz. And here's the period. Okay. And there are some calculations involved in here as well I want to talk about. And that's something about in class number 12. So we may need another session on Wednesday as well, just sit here and go through the calculations. Okay, so I'm going to change the schedule here a little bit. So we still have to meet here in the class for maybe 20 minutes or so to wrap up task 2 so you know how to do it, right? And then we'll let you guys start working on your PCB design. So we don't actually use the lab over there. You can do it in this class, right? We have the desktop over here. You can bring your laptop over here. We'll do a 20 minutes lecture, and then we'll let you guys start working on your PCB and projects. Any questions on this, the schedule? Anything else? All right. That's it for today.